For the first minute, let's dig into one of the most effective but least discussed Cold War shelter hacks ever engineered. You see, while most folks focus on steel blast doors, thick concrete walls, and radiation shielding, the true long-term survival of Cold War bunkers came down to something quieter. Not dramatic, not mechanical, and certainly not the kind of thing that made it into propaganda brochures. Yet this subtle method kept shelters intact for decades, long after their filters rusted, their generators died, and their supply caches expired. It was the quiet detail that engineers designed once and never had to adjust again. The brilliant, silent hack was the buried ventilation earth channel, a passive, ground-cooled, moisture-controlled air passage built outside the main structure. It didn't rely on electricity, didn't require maintenance, and it shaped the microclimate of many Cold War shelters so effectively that even today some of these forgotten facilities remain surprisingly dry and breathable when rediscovered. The Cold War wasn't just a race for missiles and intelligence, no, it was a race for environmental control, how to keep people alive underground longer than an adversary expected. Without constant airflow, any shelter becomes uninhabitable within hours, and yet forced air systems were unreliable, loud, and often required fuel that couldn't be guaranteed during a crisis. The ventilation earth channel solved the problem by letting physics do the work. This opening section sets the stage, because once you understand what these channels did, you begin to see why abandoned sites across Europe and North America have endured the decades far better than their modern replicas. The brilliance of the ventilation earth channel was that it used the ground as both a filter and a stabilizer. Engineers created long, shallow trenches leading from the outside of the shelter to deep within its interior. These trenches were filled with gravel, sealed with breathable layers of soil, and occasionally lined with stone or perforated pipe. Incoming air travelled through the earth before it ever reached the shelter. The soil mass cooled it, dried it, filtered it, and normalized pressure differences, all without fans. Air entering at 50 degrees outside the berm could reach the shelter stabilized at closer to the constant underground temperature. This meant lower humidity spikes, fewer condensation issues, and dramatically less mold, the silent killers of poorly designed bunkers. This system worked because Earth is naturally stable. It holds a consistent temperature year-round. Air drawn through it sheds moisture, dust, and heat. Engineers took advantage of that stability to create passive climate control before the term even existed. Many Cold War shelters that used these systems smell neutral today when opened, even after decades sealed, because the earth channel prevented the interior from becoming a stale, humid tomb. The earth channel also acted as a natural pressure buffer during external shock waves. One overlooked challenge in designing Cold War shelters was the issue of blast pressure entering the ventilation system. If a shockwave entered a pipe directly, it could rupture internal walls or violently compress the air inside, injuring occupants and compromising seals. The earth channel solved this with distance and resistance. A long, indirect pathway filled with earth, gravel, and natural filtering materials absorbed pressure variations, dampening shock waves to survivable levels without relying on delicate mechanical valves. This is why command structures in Europe and hardened communication bunkers in North America preferred this system over direct intake pipes. Buildings with earth channels often retained structural integrity even when later demolition attempts were made. Pressure simply bled off harmlessly into the soil. That passive resilience is rare in modern builds, which tend to rely on mechanical dampers that require servicing and eventually fail. The silent success of the earth channel becomes most obvious when you compare it to failed modern imitations. Many contemporary bunkers use short PVC intake pipes surrounded by waterproof membranes. These look clean and efficient on paper, but they create two problems. First, they offer no thermal buffering. The air enters at ambient temperature and forces the shelter to fight condensation constantly. Second, they create direct paths for pressure and moisture. Cold War engineers solved both issues, not by adding equipment, but by extending the pathway and letting the earth do the heavy lifting. Anyone building an underground structure today, whether a root cellar, a storm shelter, a long-term pantry, or a small homestead bunker, can still use this Cold War trick with modern materials. The method is simple. Excavate a shallow trench stretching away from the shelter's intended intake point. Fill it with coarse gravel or a mix of stone and perforated pipe. Cover it with a breathable soil layer. The goal is not to waterproof the channel, but to let the earth interact with the air. Then run the intake opening into the deepest part of the channel, not directly from the surface. What you get is a steady, cool airflow that remains far more stable than any direct mechanical intake. This Cold War technique also works perfectly for stabilizing storage rooms and food preservation spaces. Many homesteaders struggle with inconsistent temperatures in underground pantries. They install fans, dehumidifiers, or chemical absorbers. But a small earth channel can do the job with no electricity at all. Air that travels through a gravel trench enters at the Earth's natural temperature range. In cold climates, this keeps root cellars above freezing. In hot climates, it cools the space enough to prolong shelf life. Historical sites demonstrate that these systems kept ammunition, documents and sensitive equipment usable long after their expected lifespan. The enduring lesson is that the quietest Cold War engineering solutions were often the smartest. The ventilation earth channel required no moving parts, no fuel, and almost no oversight. It simply worked, year after year, decade after decade. Engineers who designed these shelters trusted physics more than machinery. And that decision is why many of their structures perform better today than expensive modern ones built with advanced materials but poor environmental planning. If you value deep historical engineering insights with real applications for today's world, make sure you subscribe to In the Beginning and share this video with others who appreciate serious, well-preserved Cold War knowledge. The past still offers some of the most reliable tools we have.